to class, everybody. We're not going to talk about the Cybertruck, right? Naturally, we have to say a few things about this. So, raise of hands, who watched the demo last night? Did anybody? A few Tesla fans out there? I watched it with great interest. You should watch it. If anything, it will you'll take away a couple things. First off, you cannot just be brilliant and not be a good communicator. Every time I see Musk, who's a brilliant person, I think, pitch, I'm reminded how much he needs coaching to be a better public speaker. Because it's painful to watch. So that's one reason I think worth watching it. Second, you should double, triple, quadruple check things before your pitch, because if you hadn't seen this, the truck's amazing. It's interesting, I think. But they have stainless steel. They call it a new alloy that they've developed in-house, the same one they're using on Starship, the big gleaming metal spaceship they're doing. It's called 30X cold rolled hardened steel, right? I don't know what the 30X means. That could be a throwback to like samurai swords where they would fold them X number of times and it gets harder and harder. It could be dimensionality reduction. We know that things get harder when you cold roll them, so that could be somehow riffing on like the change in the elongation, which is a measure of how far they've cold rolled it. I have no idea, right? But they have a pretty awesome metal alloy. They smack it with sledgehammers. It looks pretty good. It's not denting and scratching. So this is exactly what you'd expect from a CEO who was a material scientist, right? This guy went to grad school for like a year before dropping out, but he was doing material science before he did drop out, right? And then the windows, even more interesting. The windows, they say it's not regular glass, it's transparent metal, right? What does that mean, right? We have transparent conducting oxides today, things like zinc oxide. Zinc oxide, for example, will be transparent and it will still conduct electricity as if it were a metal. Or there's other things like indium tin oxide. I guarantee this is not indium tin oxide. That would be bonkers expensive. And you don't need it to conduct electricity. But there are lots of things that could potentially be better than glass. Glass is not the highest toughness material out there. There's lots of ceramics, polycrystalline ceramics, which could have higher toughness than glass. So I don't know what they've actually used, but the demo is worth watching because it was amazing. They've got big plates of this stuff, the size of this table, maybe in half. And they take these big metal ball bearings and they're dropping it on it. It's not shattering. It's not cracking or anything. It's pretty impressive. They drop it from higher and higher. They're pretty big ball bearings. And they're so convinced that they've made something that's, that's literally bulletproof. They shoot this with 9mm and the bullets shatter, right? This is pretty cool. Not the windows, the steel. But the windows, they're saying, it's amazing, it's unbreakable. We built it, not Ford tough, but actual tough. Like it was a pretty good burn they got in. It was a pretty good burn until they actually tested this out. The guy takes it, winds up, chucks it at the window, and come on, Google, you know what I want. It was so great! It was the single greatest moment of any product release in your lifetimes. Go back and watch this. I'm sure you can find it on YouTube. He chucks it and it shatters, and he was visibly stunned. There was actually a hot mic moment. If you listen close, it's pretty entertaining. Like, oh, shit. And he's just like, you take a bad speaker and then you throw like worst case scenario. Our truck is indestructible, and then it destructs on like a pretty softball throw. And then it's like, oh no, let's try it again. Again, it breaks the other one. Do yourself a favor and watch it. I won't spend any more class time talking about this. It was glorious. It was Elon Musk at peak Elon Musk. And can we talk? We don't have time to talk about it. But how about those body lines, right? Am I right? Them body lines. It's built for space. The official truck of Mars, I think he said today. Pressurized, yeah. Tyler? Very much an accident that the window broke. We don't have any more information than the 20-minute demo that was released last night. More information is forthcoming. When mine comes, I'll tell you about it. All right, our learning objectives for today. Apart from mocking a delightful product release, we're going to talk about conductivity, electrical conductivity in ceramics and polymers. We've already talked about this a little bit today, right? I've just told you that there exists metals that conduct electricity but are transparent. Those are actually ceramics. They're no longer metals, they're ceramics. They behave like metals. We'll dive into those a little bit today. There is this idea of dielectric materials that we need to introduce. What are dielectric materials? What do we use them for? We'll talk about polarization. We'll talk about mechanisms of polarization and rank them in terms of their response as you change time, the time constant there. We'll describe what is dielectric breakdown. And if we have time at the end of class, we're going to introduce piezoelectricity. It's piezo, not piezo. Piezo. I watched a very bad Christmas movie called Santa with Muscles, and they called it piezoelectric crystals the whole way through the movie, and my brain almost exploded. And they do not explode, although they did in the movie. We'll see real life what they do but at the end of class today. It features Hulk Hogan as Santa Claus. It's all you need to know about this movie. Okay, metals can clearly conduct electricity. You've got free carriers, copper, aluminum, lots of free electrons which are not tightly bound, so they can slosh around. And if you apply an electric field to them, they will move in response to that electric field. But other materials can also become conductors. We talked about semiconductors, and we said an intrinsic semiconductor, if you just heat it up enough, the electrons will start to jump the gap, and now you've got carriers. And so they will also become conductors. Or you can dope them. If you dope them, you intentionally make that gap that they have to jump much smaller. And based off of the numbers of dopants that you put into it, which you can control, because you can diffuse them in or ion implant them into your material, you can basically dial in the exact concentration that you want to get the exact conductivity that you want, which is pretty slick. So other materials can also conduct electricity. Ceramics and polymers are not typically things that we think of as being conductors of electricity. They are typically insulators because they have a really big band gap, right? So how do you make them start conducting? You get creative. One thing you can do is you can make them conduct electricity not via electrons, which would have to overcome a really big gap, but instead via ions. What's the difference between an ion and an electron? Well, ions can be things like our YSZ that we talked about earlier this semester. YSZ, what did that stand for again? Yttria stabilized zirconia, right? So this started out as zirconia, ZrO2, and we took out some of the zirconium and we put in yttrium. And since the yttrium is 3+, and this guy was 4+, to have charge neutrality, we had to introduce oxygen vacancies. So this material at a microscopic level, really, really zoomed in, atomic level basically, you have a bunch of missing spots where you have oxygen vacancies, right? This material is riddled with oxygen vacancies. It's the Swiss cheese of oxygen vacancies. And so then, if you introduce oxygen ions, an oxygen 2- ion is able to travel through this material. So oxygen 2- ion is an ion. It's not an electron. It has a charge. It has a 2- charge. So if it can travel through your material, you just made an electrical conductor. It doesn't get electrical conduction via electrons moving through it, but it doesn't matter because these things have the charge of 2 electrons, right? So if they move through it, it will still conduct electricity, right? Or you can use it in similar applications, I should say, okay? So these ion conductors, they can be negative or positive. There exist proton conductors, which will conduct H+ ions. There exist oxygen ion conductors, and lots of other things, sodium ion conductors, lithium ion conductors. You can design lots of different ceramic materials or polymer materials which happen to conduct ions pretty well. So what does your electronic conductivity look like? Your overall electronic conductivity technically should include 2 contributions. That from electrons moving in it, that's going to be your electronic component. In these materials, that is 0. In fact, they designed them to be as close to 0 as possible. We don't want electrons to move through them because we use them for batteries, right? Or fuel cells. In those scenarios, let's take a fuel cell for a minute, okay? In a fuel cell, you've got your, oh gosh, no, I did it. All right. You've got your YSZ membrane. YSZ, that's going to be the thing that conducts oxygen. You've got your anode and your cathode on either side, so we'll call this cathode, and this guy over here, we'll call it anode, okay? So in comes, I'm going to get this wrong, let's see if we get it right. You've got O2-. O2- picks up electrons, so this thing is going to add electrons to become O2-. If we have half of an O2 molecule, so that gains electrons. If it gains electrons, that's a oxidation or reduction. Reduction, and this is at the cathode, so we got it right. the reduction reaction occurred right here, right? So it had to get electrons from somewhere. Where did it get electrons from? From the other side. From the other side, these electrons go out of your device, and they come over here. So your electrons are traveling that way. Your oxygen ions, as now 2 minus form, are traveling that way. When they get to the other side, they're going to surrender their electrons. You have oxygen 2 minus turning into 2 electrons plus half of a molecule of O2 gas, right? So as long as you keep on providing oxygen over here, and you keep on using that oxygen over here, this will just keep on happening. Your electrons will travel outside of your device and through your cybertruck, right, or whatever, to power your iPhone or cybertruck or whatever, right? Those electrons, it's imperative that they travel outside of this material. Because if they just travel, if electrons could do this, technically these reactions could still happen just like they're written, but that doesn't do you any good because there's no external work done. Your electrons traveled right through your device, so this is just going to heat up a little bit. It's not actually serving any purpose for you. But if your material does not conduct electrons and instead they have to travel through some device, an external circuit, you have a useful application of this. Are there questions I can answer about this? Nope? Yeah, Jaden.
It's the electrons that have to travel around it that's like basically going through the wire.
Yep, the electrons exit the device here and go through wires, through your cell phone or truck or whatever it is, to, like, that's the current that you need to power your devices. Okay? So this will only work in as much as you have a regular source of oxygen over here, right? And you can get rid of that oxygen on this side. Because once it reaches equilibrium on both sides, if the partial pressure of oxygen is the same on both sides, then you no longer have a driving force for oxygen ions to travel that way. And there you no longer have a driving force for electrons to do the circuit, right? So you have to have a source of fuel, and you have to keep on depleting that fuel, or it will not keep on giving you power. Okay? Abby? Nope, no band gaps here. These are actual solid materials. I'm showing you, so what these look like, fuel cell SOFC cross-section. We're looking at the cross-section of a solid oxide fuel cell, SOFC. If you look at these things, I used to make them when I worked at Ceramatech years ago. It looks like this. You've got a dense layer in the middle. That's your electrolyte. That's what conducts the oxygen ions. It has to be dense because if it wasn't dense, a gas could flow through it. You can't have that. You have to have only ions flowing through it. And then you've got these really porous layers on the top and bottom. Those are porous because this is where you have to have both electrical conduction, you have to have electrons shuttling in and out of these things, and you have to have gas permeating those. And you basically want to have as many points as possible where you have electrical contact in contact with a gas phase and connection to your electrolyte. So it's called a triple junction, a triple point. So let me find a better picture of that. It looks something like, let me find a good picture of it. I don't have a good picture. I'll find one after class. But that's how these things work. I'm literally showing you a cross-section of it, okay? The way I've drawn it here, this thing's massive. In reality, you don't want that to be very resistive. You want to make it as easy as possible for oxygen to travel across that. You can do that in two ways. You can increase the conductivity of this material, or you can make it thinner, right, to get the maximum flux across it. And they do both. They try and make it as conductive as possible by hiring folks like us, right, to make them new materials. And then they make it as thin as possible by strengthening it so that it doesn't break even though it's really thin, by hiring folks like us as well, right? So the ionic conductivity is what these things rely on. They rely on their total electrical transport, electrical conductivity, having as much being ionic as possible and as small as possible being the electronic, right? You might want it to actually conduct both, and there's materials that do that, like cerium oxide will conduct both oxygen ions and electricity. It basically has like a partially filled band, so it looks kind of like a metal, but it has lots of vacancies, so oxygen can also travel through it. You use that for these upper and lower regions. This would be something like a mixed ion conductor. This would be just ion conductor. This would conduct electrons and ions. This would conduct just ions. Everybody with me so far? So essentially, the total conductivity you're going to get is going to be proportional to the charge that each of these can have. So if you conduct oxygen, which is 2 minus, then you're getting more bang for your buck than if you were to conduct chlorine, which is 1 minus, right? All things equal, if the diffusion rates are the exact same, you're getting twice as much from the oxygen as you would from chlorine. So sodium batteries and lithium-ion batteries, those are both 1 plus. So you get some benefit, but there's a lot of research right now looking at magnesium batteries. Why? Well, if you pull up the periodic table, which we know and love, and you look where magnesium is, it has the potential to be much better because it's a column 2. When magnesium turns into an ion, it's typically magnesium 2 plus. So every time that you shuttle a magnesium ion across your battery, you're getting 2 electrons that have to travel through the external loop as opposed to just 1. So these could potentially store lots more energy. You could get much more capacitance because of these things, right? They have their own problems. The biggest problem is that we don't have great electrolyte materials. We don't have great materials that conduct magnesium ions, right? So there is active research all over the place, people trying to come up with, like my friend at Caltech, she's working on these, but basically they're trying to find materials that conduct magnesium 2 plus ions. And that's a big engineering problem because with oxygen ions, it was easy to make an oxygen vacancy. Now you have to engineer a material that has magnesium vacancies, and that's a little bit trickier to do. They can make them, but they're nowhere near as good in terms of conductivity right now. Future batteries will probably use this technology. I think it's very likely. In fact, you could even get crazy. You could say like an aluminum battery, where the aluminum ion travels across it. It's now 3 plus. You could get triple the benefit. This has lots of other engineering challenges, right? It may or may not work, but these are future directions for batteries based off of this idea of changing ionic conductivity. Polymers, you would not expect polymers to be good conductors of electricity for a couple reasons. First off, they have big band gaps. Second off, if you look at them, polymers are these like spaghetti chains, mostly not connected to one another. They might tangle, right? But that's not like a good electronic bond. It's usually like a tangle with the occasional cross-linking. So where are your electrons going to travel? Even if you could get electrons in this thing, they're going to travel along the backbones. And so it's just not a good recipe for a good conductor. Nevertheless, in the 70s, Alan Heeger at UCSB won a Nobel Prize for this work. He figured out a way to make them conduct along the backbone. He basically said if you have alternating double bonds, single bonds like this is the key component of any conducting polymer, is what they call this conjugated segment, this alternating backbone. What it leads to, here they're drawing their orbitals in a way that we haven't drawn them very much in this class. This is the Z, the PZ, so it's your p orbital. Remember in the p orbital there was 3 orbitals. In the p shell, I should say, there's 3 orbitals. One of them is in the z direction. It points up and down. If you alternate them like this, then this is half-filled. You have a half-filled band, right? Anytime you have a half-filled band, we should all be saying, bingo, that's a metal. And in fact, they discovered metals, right? So it went from being totally impossible to Nobel Prize winning, and now it's all over the place. Conductive polymers are not even like a thing anymore. It's like it's common now. Nowadays, we can even do crazier things. We can make OLEDs. If you've seen a TV that says OLED, what does that stand for? It's an organic light-emitting diode. So they made semiconductors out of polymer materials that you can bend, right? This is a diode. You can see the light coming off. Why does light come off again? Remind your neighbor, why does light come off when you put together different semiconductors? Remind your neighbor. Okay, somebody remind me. How do these things work? Why is light given off? What's happening here? Anybody? All right, Jared, I'm going to pick on you. What's happening? Somebody phone a friend. All right, Alan, you want to help him?
We'll see if this is it. But essentially, it's like as it's jumping between the valence band and the conducting band,
Yep.
it has a discrete level there
Yep.
still because it is still a band. And
Yep.
so it gives off that energy in the form of light.
We said this last time. That's exactly right. You make the whole amazing thing is that they made polymers, which are semiconductors, meaning they technically do have band gaps between this is your valence band, which is filled with electrons totally to the brim. And then you got your conduction band up here, which they've populated with some number of electrons by doping it. So this would be an extrinsic polymer semiconductor. And then you got this opposite over here, you've got p-type. If you direct the current to go electrons that way, holes this way, so if the current's going that way, electrons are going that way, they're going to enter the material next to it, and they're going to say, hey, why am I going to travel up here when I could drop down and fill these spots? I can go down in energy. Everything wants to do that. But in doing so, it has to drop down a discrete amount, and that's the light you're getting off. And in the picture you saw, it must have been a distance corresponding to a green LED. So we know that we can make these out of semiconductors. We've been making these for a long time. It hasn't been that long that we've been making them out of polymeric materials. But we can. We can do this today. This is not even like a futuristic technology. You can buy these today. Abby?
Since the band gaps in conductors, semiconductors, etc. are different,
Yep.
does that mean that the light emits from electrons?
Yeah, the color of light that you get out of these will be proportional to the band gap distance. So if you want a really bright green light, you need to make sure your band gap is exactly, I think it's like 2 electron volts or something, whatever it is that corresponds to that color of light. And if you change the band gap separation, then you'll change the color of your light. Now, it's not like everything else is equal in these. The efficiencies aren't necessarily the same here versus a semiconductor that's not a polymer. So efficiencies are not coming into this because what do I mean by efficiencies? It means what fraction of your electrons that you try and send through here actually drop down. Maybe some make it all the way through. And that means that your device just heats up and you don't get any light coming out. That's a less efficient LED. So not all materials are created the same in that respect, but all of them can be doped like this. And right now, this is allowing us to make devices that we could have never dreamed of before. If you remember the Samsung Note, have you seen the pictures of the new foldable Samsung Note? Have you seen this? This uses OLEDs, which are technically flexible. It is one sheet that is flexible. Now, it's having problems. Those things are breaking. It's not a great idea to fold any sort of electronic because fatigue. We learned about fatigue in this class, right? Repeated stress. Cyclic stress is not a great thing. Things fail by fatigue typically, and that's happening, but it's getting better all the time. The things they can do out of this is getting better all the time. You could have, some of the benefits of this is they can do roll-to-roll production. Instead of growing a big single crystal of silicon, which is what we do right now, Czochralski growth, you guys are all learning about crystal growth right now. You can tell me how hard it is, right? Instead of doing that, you can just make a big batch of this liquid slurp, start pulling it out, and you can just keep on extruding a big continuous film of it. That means cost is really low. So organic photovoltaics are already a thing you can buy, and their cost is going down, 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 down. It might reach the point where their efficiency and cost makes them the more attractive option compared to traditional materials like polycrystalline silicon. That's not here today. They're definitely not as good yet, but who knows what happens. Pramit? How do you make them conduct? It has everything to do with the chemistry that you choose in the bonds. The key thing, the only thing I'm expecting you to know in this class is an alternating double, single, double, single, double, single bond. What that does is it leads to your p orbital. Orange means filled, white means not filled. You can see that these are half filled. You have a half filled band. So your electrons hop from orbital to orbital. That's how you get conduction. So it's a very simple picture. There's much more complex description of it that we won't do in this class. Yeah, Tyler?
Talking about the efficiency of the LED, is that like the same as the resistance?
Yeah, you could say that one is more resistive than the other. Or the term that they typically use is quantum efficiency. Like what fraction of your quantum interactions, meaning electron drops down, fills the site, and gives off energy, it's a quantum interaction. What fraction of that actually happens versus just not happening? Okay, any questions about anything we've covered so far, Josh? The band gap. The color of the LED is based off of the band gap. So for example, if we were up here with our LED, if I'm green and I want to turn into a red LED, if I want to change something, what I need to do is green, if I look at my EM spectrum, you got to ask yourself, okay, where's green at and where's red at? So if I look at this, red is on the longer end, green is on the shorter end. Longer means lower energy. Longer wavelengths are things like way over here, like radio waves, right? Millimeter wave that you do like at the airport. That's all long wavelength. It's low energy. Things over here are like X-rays. Microwaves are where? Microwaves are on the right-hand side. Anyways, you want to go lower in energy. So in your band gap, you don't want this gap to be as big. You want to make it a little bit smaller, and then you'd have a red LED. Okay? Yeah, Jared? They use RGB. So I just did this for my Pinewood Derby for my kid. RGB LED. If you look inside of an LED, oh, this is me Googling how to do this. RGB LED, period. Right? Inside of these, what you'll see is you always have these 4 different posts, right? It's always got the 4 legs on it because inside of it you have 3 different semiconductor materials. It's 3 LEDs in one. So to get the color changing one, they literally just change the ratio of these things. That's what the RGB color code means, is what fraction, if it's like 25500, that means it's complete red and nothing in these. And you can get all sorts of colors just by changing this ratio. If you do these small enough, then you don't see them. On these LEDs, actually, when you turn them on, you can see these 3 different color rings kind of coming out. But if you're far enough away, it looks white if you were to combine them all. Or if you just combine these two, it looks yellow or, whatever. Colors. Right? You guys know what I'm saying. Any other questions before we move on to dielectrics? Okay, let's keep going. Okay. Dielectrics. These are super important. Dielectrics are materials that do not conduct electricity. Okay? Just like the YSC fuel cell, remember the electrolyte? We said that cannot conduct electricity or ions. These can't conduct either. They cannot conduct either electricity or ions. Okay? The reason why we don't want them to is because for dielectrics, we want to accumulate as much charge on the surface as possible. So in physics, you've probably seen the parallel plate capacitor. Did you guys see this in physics? Yes. You've seen this before? The parallel plate capacitor is 2 sheets of metal for a minute. Imagine there's vacuum, so there's nothing in between them but vacuum. If you apply a voltage across this thing, then you can figure out what's the total amount of charge that you place on these surfaces, and they will be equal and opposite. So if I apply a voltage to this from a battery, I will accumulate negative charge and positive charge on these 2 sides. And the amount of charge that I can accumulate is proportional to a couple things. It's proportional to the surface area, so the bigger these plates are, the more charge I can put there, and to how close these things are. If it's closer, I can put more charge there, because why? Because the electric field across this is difference in voltage, which isn't changing. Your battery's still a 9-volt battery. But this distance, as it goes down, your electric field gets larger. So they wrap all this up together and they call it its capacitance. Its capacitance, C, is equal to a constant, epsilon naught. That's your permittivity of free space, which you've seen in physics before. That's the 8.85 e to the negative 12 farads per meter. That's multiplied by the area of your parallel plate capacitor and divided by the distance. So if you want to store more, if you want a bigger capacitor, and we use these all the time in devices, capacitors are everywhere. Resistors, capacitors, and transistors are like the building blocks of all of your devices, right? And if you want a bigger capacitance, then you've got to make your surface area bigger or bring them closer together. Everybody with me? What happens if you bring them too close together? Well, if they touch, then you have a wire. That's not going to help you very much. It's no longer a capacitor. And if they get really close, have you ever had like your socks on and then you go to like touch that doorknob and you get the zap? It's because you are a capacitor between you and that doorknob, and the closer and closer you get, the electric field is increasing, and eventually the electrons in your finger are on the doorknob. I don't know which one's which, but they jump from one to the other because you have breakdown, dielectric breakdown of air. Turns out it's pretty easy to send electricity through air, which sounds kind of crazy, but there's molecules, right? This is how lightning works. Lightning is the exact same thing. Big, big difference. And so the amount of current that does finally go through it is ginormous, right? Because it's a big separation. Ours is a tiny little lightning bolt because it's really close together, okay? That's when your dielectric stops doing its job. The dielectric's only job is to prevent electrical transport across these 2 things. So vacuum's not the best material for this. Vacuum will do an okay job, but you can only do better as you put something in there in that gap, as long as it doesn't conduct electricity. So we call this our dielectric insulator or dielectric material. What it does is it modifies this expression. It looks really close. Now the capacitance is epsilon times A over D instead of epsilon naught, where epsilon itself is, where do I have it? Right here. Epsilon is equal to your permittivity of free space multiplied by some constant, epsilon r, which is it doesn't have units, it's a number, right? So if you had a material that was like 100 for your epsilon r, your dielectric constant, we call this the dielectric constant. If it's 100, then you made a capacitor that's 100 times better than vacuum, right? Everybody with me? And in the old days, like World War II days, we didn't have very good materials to put in between these dielectrics. They were using clay. Clay was actually like one of the better materials. And so if you need a big capacitance, like for old radios, look up like the size of old radios, like World War II radio. Well, no, capacitor. Capacitor versus now. I don't know. I don't know if this is gonna work. I feel like I'm not on my Google game here, but like, okay. So I'm looking for a good comparison one here. The what now? Well, I'm just trying to show you that the size of the capacitors, I'm looking for the image that shows that all of these are like the same capacitance. And over time, there are images that show this. Like, all of these things might have the exact same capacitance. So what has changed? Well, what can we do? If it's the capacitance that you design around when you make these things, C, what can you do? You can either increase the area, and that's what they did back then. They would take these things, and they wouldn't make them actually parallel plates because then you'd have to have this giant thing in your device. What do they do instead? They roll it up, right? You've got this material, or you could roll that thing up, right, and then have the other one right next to it, and you could have a parallel plate distributed over some area, right? You could roll it up. That's one option. And so they did that, and these things got really big. So that's what you're seeing in some of these images is like really, they had to roll it up lots and lots and lots because the dielectric material of the day was not great. It was basically like clay. And so I think its value is somewhere around like 80. I think I have some numbers in a minute I'll show you. But it's not great. Nowadays, we have materials that have dielectric constants of like 10,000. Come on! That's pretty exciting! That's like 4 orders of magnitude better? That's huge! So what on earth is happening? Why can some materials have a dielectric constant of nothing, basically 1, and some be 10,000? What's going on? Why are some materials able to allow you to store 10,000 times as much current or charge on these plates? How do we do that? Here's how you do it. It relies on polarization. You've learned about polarization before. Polarization means you have a polar molecule, like this thing. This could be some sort of molecule that has a negative and a positive side. Water is a good example of this. Water, it looks like this. It's H2O. So you've got two H's. You've got your O. Is this a polar molecule? You betcha. How come? Well, because oxygen is more electronegative. It wants electrons more than the other ones. So you end up with this dipole. You got a positive side and a negative side. Okay? This is a polar molecule. What happens to polar molecules when you put them in the presence of an electric field? They line up, right? This thing says, if that's my electric field, where that's the negative end, this is the positive end, the positive side of your molecule lines up to the negative end of the field. The negative end lines up to the positive side of your field. You get molecule alignment in the presence of an electric field. Okay? This is polarization. Okay? So, this is what they did. They said, all right, let's take our parallel plate capacitor from before. What happens if we stuff it full of a bunch of materials that have dipoles in them? Then they're going to be randomly oriented, just kind of everywhere. But as soon as you apply an electric field across this thing, these are all going to line up. And in doing so, they take charge with them, and so it allows you to accumulate more charge on the surfaces because these dipoles lined up and gave extra charge. So here's sort of a picture that I kind of like. Again, they're randomly aligned here. They're just kind of everywhere. Like the positive and negatives are kind of doing their own thing. But here, you've lined it up in such a way that now you can store more negative electrons on this plate because of these positive dipoles that have lined up to it. Okay? Interestingly, this middle region does nothing for you. You get no benefit from all of these molecules in the middle. You only benefit from the polar molecules near the surface. So there's still a driving force to make this thing as thin as possible. Right? You want it as thin as possible that will work without having dielectric breakdown, which is when all these electrons say, to heck with it, we're going to burn our way through this material and go to the other side, which is what happens. Right, Abby?
So kind of back towards the beginning of dielectrics when you were discussing the equation.
Okay.
You said that you have, I think it's strain. Is that what we're discussing? Okay,
That's not strain, epsilon. Sorry, we ran out of, this is material science. We need like 5 more alphabets. Different strain. This is, epsilon naught is your permittivity of free space, 8.85 e to the negative 12 farad meters per meter. Epsilon is epsilon naught times epsilon r, where epsilon r is what we call the dielectric constant. It's just it's an integer. Well, it doesn't have to be an integer. It's a number. It doesn't have units. That tells you how much better your material is at storing charge compared to vacuum.
So the epsilon that we're solving for, like you said, is just telling us how much better it is at storing charge.
That's right.
That's how, okay.
Yep, and clay was like the best thing they had in World War II, and it was just okay. And nowadays we have materials which are bonkers better, which allows us to miniaturize devices, which we all want. Because nobody wants the technology that I had growing up with. You want the latest and greatest miniaturized things. We all do, right? But we have to do that by shrinking physically like the components, which means our materials properties have to get better. They have to be stronger. They have to have better electronic and whatever properties. Sam?
What happens when you flip it? When you have your
Okay. Yeah, so you have this material, and we applied our battery this way, positive, negative. So the negatives came here, the positive charge was there. If you flip the charge of this, these molecules have to rotate. They rotate.
They will?
Well, if you have a good dielectric material, and they're going to be able to rotate. If they're not able to rotate, you won't have as good of a dielectric. So the best materials out there, the ones that I've been describing, which are just insane performance, are able to shift charge really easily. Now, you could do that with molecules, which actually rotate, like a water molecule would have to rotate 180 degrees, but there's other more clever ways to do it, okay? So on the homework, you're going to calculate the charge density on surfaces. We call that D. D is the amount of charge per area, right? And there's some expressions that tell you this. It's based off of the polarization, the electric field. So you'll use that on your homework, but it's pretty straightforward explained in the homework. I'm more interested in getting to this idea of where does this polarization come from? We've shown you water molecules, right? I could switch an electric field. I could take an electric field and have it alternating, and I could rotate this water molecule. So clearly rotating polar molecules is one mechanism of increased dielectric constant. But what else is there? There's lots. For example, there's electronic. Electronic says this. You've got your atom, and without an electric field, if I could sort of take a really simple picture of an atom, we know that it's much more complicated than this, but let's assume this is like an okay idea, at least for a minute. If I take a snapshot at any given moment, this is where my electrons are, right? They would be in that spot for that moment. But when you apply an electric field to this, your nucleus is going to shift a little bit, and your electrons are going to shift a little bit, right? They're polarized. They have a charge, right? They can be polarized. And so electronic polarization is possible, where literally your nucleus shifts a little bit, and your electron cloud shifts a little bit. We're not talking about a big shift, but it is there. It's perceptible and it's measurable, okay? That's one way of getting polarization. So any atom will have some dielectric constant. This is why anything is better than vacuum. Vacuum has no atoms, so you don't get even the electronic component. That's not very useful, right? Anything you put in there, air, clay, water, will do better, as long as it doesn't conduct electricity. If it conducts electricity, you're out of luck. Pramit?
So does that individual atom volume
I don't have the answer to that. I don't know. It would make sense to me that because it elongates, maybe the volume changes a little bit. I don't have a good answer for you there. Another way of doing it is called ionic. Ionic contribution says, okay, let's start with a ceramic. A ceramic has different sized ions because you've got cation, anion, right? So these things have charges to them. If you apply an electric field across this thing, your positives are going to want to go one direction, your negatives are going to want to go the other. So they're showing in the red grid where the atoms used to be, and you can see that the positives now shifted to the right, the negatives shifted a little bit to the left, and all of these get shifted a little bit. And so lots and lots of atoms, if they're all shifting even a little bit, these have a charge, remember, that can be a significant source of polarization, okay? That's another way you can do it. And then rotation, or orientational, is what we've already talked about. So the question I have for you is our clicker question. If I can find it. Okay. The question I have for you is the following. Think about putting these different materials that have these different mechanisms at play, and then switching the polarization, right? Switching the electric field. On this side, it's positive, negative, and then you're going to switch it, right? And then you're going to switch it. And there's a rate at which you could switch these things, right? So at high frequency means you're switching that very quickly. Which polarization would you observe? Electronic, ionic, or orientational? You're switching it very quickly. Which one of these is going to be able to respond to that? Fast switch. Okay, get your answers in. Okay, we're going to close the poll. A, B, or C? Okay. Which one should respond at high frequencies? Only electronic is correct. Now, why not? To answer this question, everybody, so come on up here, Eric. I'm volunteering you. Eric's going to stand up here, and he's going to take a ginormous step to the left or to the right, depending on what I'm doing, okay? So if I raise my hand here, take a huge step that way, right? So then this way, and then this way, and then this way, and this way, and this way. So you can't do it. He can't do it. So what did you experience when I was trying to make you switch too fast?
Well, my legs hurt.
Your legs hurt? We could say frustration, right? We call this dielectric loss. You can take a seat. Dielectric heating occurs. You literally heat things up. If you're switching too fast, then Eric's just like, I don't care, I'm not going to bother. Which you saw happen. He's like, I'm not going to do that. Atoms do the same thing, right? If you go too fast, they're like, no. And if you go too slow, then they just respond. It's in that intermediate range where they're like trying to keep up, where it's right at the bubble. That's where you get your maximum loss. What do we care about loss for? It heats up. When you have loss, you get dielectric heating. Where do we use this? Andrew knows. Where do we use this, Andrew? Oh, he was surfing the internet. Where do we use dielectric loss? Why is this useful? We did a podcast episode on it. And you spoke half the time. He looks like Elon Musk did when the windows broke. Yeah. Hint, they do it with water. It's specifically designed the frequency to match up to water molecules rotating. Microwaves! This is how microwaves work. Microwaves, you're relying on an alternating electromagnetic field, right? That's going to cause your water molecules to rotate. And if you tune it to just the right frequency, the water molecules are barely able to kind of keep up. And in doing so, they generate a lot of heat. And you can locally heat up water molecules, and you don't heat up the paper plate or the ceramic plate that it's on, because those don't have water molecules in them, right? So you can make just your food heat up, but not anything else. Okay? That's dielectric loss. Let's go to our next one. I think we have one more question. Okay, how about this? What polarization would be observed at both low and high frequencies? So if you switch it really fast, you see it. At low and high? I think I messed this question up. I'm just going to end it. So type an answer in and I'll give everyone credit. I think I messed that one up. Top hat got the better of me. So get something in. I will make sure that anything you type in is worth full credit. Okay, I'm going to close the poll. Answers in? This is a freebie. All right. So at low frequencies, you should only see, you should see all three, I should say. At low frequencies, if you switch slow enough, electrons can definitely respond. They move the fastest. Electronic transport. At middle frequencies, your electrons are always going to respond, but now you start getting ionic motion because ions just have to shift a little bit. And at really low frequencies, that's when your whole big molecules can rotate. Okay? So your overall polarizability, your overall performance as a capacitor, it depends on a function of frequency. This is how band pass filters work. In electronics, did you learn about filters? What's a filter do? Anybody do car stereos or anything? Is that a thing anymore? My dad put food on my table doing that growing up. So filters, if you want a tweeter versus a sub, the incoming signal, you want to split the high frequency stuff from the low frequency stuff. So you can send the long wavelengths to your amp, like your sub, and you can send the high frequency to your tweeters or whatever, right? Do they call them anymore? Anyways, right? The way they do that is you have to have a material that will only allow certain frequencies to pass through. And you use capacitors to do that. High frequencies will get through with only electronic ones. Low frequencies, medium, all of them will go through at low frequencies if you have these materials. So you can tune your material to only allow electrical signal to get through based off of what type of polarization mechanism is in place. That is how most filters work, bandpass filters work in electronics. Okay? God, we're almost out of time. Let me say a few words about dielectric breakdown. Materials, if you bring even the very best dielectric together closer and closer and closer, eventually you'll get that little lightning bolt, right? In air, you can see it as a shock. With the arc melter in our lab, we have a big arc melter, which is just like a little tiny controlled lightning bolt, but it's still the same thing in air or argon. But you can also do it in solids. So this is glass. This is glass. They put copper tape all around the outside of it, except for on this side. And then they put an electrode here, and they put a huge voltage between this electrode and the copper electrode. And what you saw is that when they increased the voltage enough that the electric field was large enough, this material just melts in all directions. It melts right through your material. In that case, they stopped it right before it hits the ends, but that's what it looks like. Yeah, Chase?
Semi-related question. So there's a video that's been going around that I've seen where they do something with like it seems like a super high voltage onto like a little glass cube, and then it, like you can see like lightning kind of esque flashes, and it'll like continue to go even after they remove it.
That might be polaronic, which is a different thing. I'd have to see the video to know for sure. That might be a polar, where you get confined electron states on the surfaces. So that might be something else, which we won't get into in this class. Send me the video and I'll send my comment. What does this look like? If you have a material that's not supposed to conduct electricity and it starts to, it's typically because you got this happening. It's local melting. You passed such a large current right through your material that it just melts everything. You made a tiny little arc, you made a tiny little welder, and it just destroys your material. Okay? That's dielectric breakdown. Okay? To prevent this, you have options. You can either pick a material that has a stronger dielectric breakdown, right, that's more resistant to this happening, or you got to make your device thicker. Those are your only options. Okay? What are some typical values? So polymers have dielectric constants of about 4, ceramics 3 to 10, and then these titanates have up to 10,000. They just have bonkers dielectric constants. We don't have time to get into it, so I'm going to spend one more day on this, or at least a half a day. The next class, though, we're going to dive into sustainability. Sustainability, I think, is important as engineers. We can't just design products that are like the best performing at the lowest cost. We have to think about the materials that we make and what that does to the planet and the world we live in. So we're going to do a whole segment on sustainability. So I'm going to assign some readings. So watch on Canvas. I'm going to assign some readings, and you need to do those readings before you come to class in order to get credit on the clicker thing. So do the readings ahead of time. We'll do that next class.